In this video, we'll discuss quadrilaterals. Now, a quadrilateral is a polygon with 4 sides, and the interior angle measures of a convex quadrilateral sum to 360 degrees. Now, let's look at some quadrilaterals against those that are not. Here, all the sides are segments. They're closed and connected. Here we have curves and open segments. So we can see the difference even with a concave quadrilateral. Now, within the quadrilaterals, we often talk about some very specific quadrilaterals, the first of which is the parallelogram. And a parallelogram is a quadrilateral for which the opposite sides are parallel. Because of this relationship, the opposite sides are congruent, the diagonal interior angles are congruent, and the consecutive angles are supplementary, and the diagonals will bisect each other. So let's use some values to help us understand these relationships. So if I said that AB was 6 units and BC was 12 units, that means that CD would have to be 6 units and AD would have to be 12 units because the opposite sides are congruent. And if I knew one angle measure, I could find the other 3 interior angles because the opposite angles, those diagonal angles, are congruent and the adjacent ones are supplementary. So angle C in this case would have to be 70 degrees, and then angle B and angle D would have to then be 110 degrees. And if I added all 4 together, I would see they sum to 360 degrees. Now, if I constructed the diagonals inside, I would see they bisect one another, so that if BE equaled 10, I know that ED would equal 10. And if I knew that the entire length of AC was 14, I would know that AE and EC would both have to be 7. Now, the second quadrilateral we'll talk about is the rectangle. And this is a special parallelogram. So it's a parallelogram where the angles are all at right angles. This is unique because it makes both the diagonals be congruent to one another. So in this case, say we have that GK is 5 and GH is 12. I know just like the other parallelograms that HL is 5 and KL is 12. But what happens here is, what if I want to know what GL is? What I recognize now is I have a unique relationship. This is a right triangle. And since it's a right triangle, I can use the Pythagorean theorem to help me find my diagonal. So I know that GL squared will equal 5 squared plus 12 squared. And I go through my simplification, and I see that GL would have to be 13 units. Now, the third quadrilateral we'll talk about is the rhombus. This is another unique type of parallelogram where all the sides are congruent. And what makes this unique then is that the diagonals are perpendicular to one another, thus forming 4 congruent right triangles inside the rhombus. Additionally, the diagonals will bisect each of the angles at the vertices. So let's look at some examples. Say that MP is 10, then I know each of those 4 sides of the rhombus are all 10 units. Now, what if I told you that PK was 16? I would know then that PH and HK would both have to be 8 units. And then the question may come, well, what is MH or even MJ? Well, because we know the diagonals are perpendicular, I again have a right triangle that I can use the Pythagorean theorem to help me find the length of MH. So MH squared plus 8 squared will equal MK squared, which is the 10. And I simplify this, and I'd find that MH is 6, therefore MJ would be 12, and HJ would be 6. Now, if I knew information about the angles, because it's a parallelogram, if angle M is 120 degrees, I know angle J would have to be 120. Angle P and angle K would both have to be 60 because they have to be supplementary to that adjacent angle. Now, what if I put in the diagonals? What I recognize is that the diagonals are going to bisect each angle. So if this was 120 and 60, the 60 degrees would become 30 and 30, which means this one is also 30 and 30, and these would each become 60 and 60. And that what we recognize here is the thing about the individual triangles, 30 plus 60 plus 90 is 180 degrees. So each of these triangles adds up to 180 degrees to also verify that all these relationships have to be true. Now the fourth special quadrilateral is the square. And this is a special parallelogram that has 4 right angles and all sides congruent. In essence, a square is a rectangle and a rhombus combined. So what this does is it makes the diagonals be perpendicular bisectors of each other and of each vertex, thus constructing a 45, 45, 90 triangle in each case. So if I know that TR was 8, I would know that the other 3 sides would also have to be 8 units. And if I drew in the diagonals, I wouldn't need to know any other information because the diagonals are congruent to one another and they are perpendicular to one another. Thus, I know that if I'm trying to find TL or LR, they are the same measure. So as I'm doing my right triangle, my Pythagorean theorem, I may start with TL squared plus LR squared, but I recognize they're the same, so this is really 2 times the length of one of those sides. So in this case, I divide by 2, then take the square root of the remaining side. So when I simplify a square root, I just want to make sure I leave the radical in most cases, and this will simplify down to 4 to the square root of 2. And that's a unique relationship that you see within the special right triangles that are 45, 45, 90. So if I know that TL is 4 square root of 2, I know that all the other individual segments are also 4 the square root of 2. And I have all the measures then of the square. Now when we classify, we can use the Venn diagram to help us recognize the relationships in the quadrilaterals. First and foremost, we have all quadrilaterals. Within that, we have a special group called parallelograms, and there's space on the outside because there's quadrilaterals that are not parallelograms. For example, there's trapezoids, there's concave quadrilaterals, there's other random shaped quadrilaterals that may exist. But then within parallelograms, there's a smaller group of rectangles. Again, there's parallelograms that are not rectangles, but all rectangles are parallelograms. And even then, there's also the rhombi. They're a special group of parallelograms, but not all parallelograms are rhombi. And we see that there's overlap between these two because inside there is our unique group of squares. Squares are both rectangles and rhombi combined. So we can look and use this relationship to help us understand how can each of these different classifications relate. So I want to know, are all parallelograms rhombi? So here's my rhombus, but I've got parallelograms. That's the larger group. So it's actually the other way around. So this is not true. Are all rhombi parallelograms? Well, if I look at the oval for rhombi, it falls inside parallelograms. So that means all the rhombi are parallelograms. What about, are all squares also rectangles? Well, here are the squares. This little subgroup of squares falls inside the oval for rectangles, so yes, that is true. And the last one, can a square be a rectangle but not a rhombus? Well, here is my group of squares. They are all rectangles, and if I look, it falls inside the rhombi, but there's no part of the squares that's outside the rhombus as well, so no, this is not possible.